Welcome to Lecture 3, The Sky, Ancient and Modern Astronomy. As the title suggests, today we're going to continue our sort of drive through the introductory portion of the class, where we kind of lay the groundwork for future investigation. We're going to introduce a number of concepts and pieces of terminology related to the sky and how it was viewed in ancient times and how it's viewed today. As it turns out, a lot of continuity of terminology in terms of the descriptions that were used in ancient times are very often continued to be used today, even as our understanding of what's actually going on with the sky and astronomy has evolved. And so we'll talk about that. We'll talk about what the ancients did, what we do today, and some similarities between the two. So one of the things that I mentioned in the first lecture is that, astronomy, as I have argued a couple of times now, is arguably, anyway, the oldest science. It's been around for a long time, and it's been around for a long time around the world, across civilizations, across cultures. And it has been, basically every advanced civilization that we have found remnants of, we have found indications of very often advanced astronomical knowledge, that really is astounding from a modern perspective, that they were able to discover and observe such detailed things without modern technology. And so here are just a few examples, here that we have. Stonehenge is obviously very well known, and the British Isles, the Mayan people were certainly very advanced in their study of astronomy, and it formed sort of a very critical aspect of their understanding of the universe, their place in it, and they had a very sophisticated calendar that was formed around it. The Persians were very advanced as well. For example, famously, the Magi, from the east, the wise men that came to visit Christ on his birth, did so by, they spent their lives looking at the stars and analyzing them. And then Beijing as well, the Chinese, certainly spent more than their fair share of time studying the sky as well. And so I admit I am not, my training is in physics and in astrophysics, and so I am not a historian of astronomy by any stretch, but there's certainly a lot of interesting history there. So if you're interested in that, by all means. So I've made the claim now, and we'll see some examples, but I've made the claim that the ancients were surprisingly good at astronomy and did a lot of sort of very impressive calculations and observations without the advantages afforded them or that would have been afforded them, that are afforded us by modern technology. And this is one great example. And this is an example that I confess I was unaware of until I first taught this class. But I've been, very impressed by it ever since. And this is the first observation, the first measurement of the Earth's radius. And so it was made by a Greek astronomer named Eratosthenes. Try saying that 3 times fast. But before I dig into the details here, the first thing that I want to point out is something that is very often misunderstood or misconstrued, which is that for the longest time, no one thought the Earth was flat, or at least no educated person thought the Earth was flat. It has been known that the Earth is spherical for over 2,000 years. So the ancient Greeks knew that the Earth was spherical, and on since then. So there certainly have been isolated people, and in fact, you can still find people that will swear to you that the Earth is flat. They're relatively few in number now, but this was very much not a discovery of Christopher Columbus. It was well known, certainly by his time, that the Earth was spherical. So even 200 years before Christ, Eratosthenes is living in Libya, so North Africa, and he decided he'd be interested in knowing, how big the Earth really is. Okay, and he made what turns out is a pretty phenomenal observation. And in particular, he noticed that when he was in the African city of Syene, on a particular day at 12 noon, the sunlight went directly straight down the well and hit the bottom, illuminated the bottom of the well. I don't remember how, in fact, I don't think I ever knew how deep the well actually was, I don't know if that's known at all, but it's fairly deep. And he just happened to notice that the sun hit the bottom of the well. And that was important because what that meant is that the sun was directly overhead. Okay, because if it was coming in at an angle at all, it would have hit the side of the well and not traveled all the way down to the bottom. But it did hit the bottom of the well, and so he said, "Oh, that's interesting. That means the sun is directly overhead." And furthermore, I don't know how many years he made this observation, but he observed that that this occurred every year on that day. So I don't remember what the day is. Imagine it was June 17th. So on June 17th, every year, at this well in Syene, the sun's light at 12 noon hits the bottom of the well. So one day, some subsequent year, on June 17th, he happens to be in Alexandria, and he thinks to himself, well, that's interesting. Today is the day that if I were in Syene, the sun's light would be, shooting directly down the well at 12 noon. And he happens to see there's a tower, or a relatively tall pillar in Alexandria that day. So he says, well, since I'm here, I might as well, I'm kind of curious, let me go out and watch at 12 noon and see how the sun's light hits this pillar. And what you might have expected is that if the sun's coming straight down in Syene, the sun, is probably coming straight down in Alexandria. But if that were the case, then there wouldn't be any shadow, right? If you have a pillar and you have sunlight coming straight down on top of the pillar, it doesn't cast any shadow, right? But if it's coming in at an angle, then of course the sunlight is blocked by the pillar, and so you get a shadow. And lo and behold, it turns out that there is a shadow cast in Alexandria. Okay, so it may or may not be obvious, but this is a big deal because what it means is that when the sunlight is coming straight down at Syene, it is not coming straight down at Alexandria. Okay, and the implication is the Earth must be curved, because if the Earth were flat and the sunlight, and so you have a flat Earth and the sun is up here sending down the rays, the sun is so far away that the rays are all going to be essentially parallel, as is represented in this picture. So the sun's rays are all coming in parallel. So if the Earth is flat, then if the sunlight is coming in perpendicular to the Earth at one place, it's going to be coming in perpendicular at the Earth in another place. The fact that that's not happening means the Earth must be curved. And in fact, he was able then to measure the angle of the shadow being cast. Turns out it was 7 degrees. And so he said, well, if the angle of the shadow is 7 degrees, you do a little bit of geometry. The Greeks were very good at geometry. And that means that there must be a 7-degree angle between radii of the Earth drawn to Syene and to Alexandria. And so just a little bit more geometry, and this is all stuff that you may not have done geometry recently, but if you were back in your high school geometry days, you could have done this. You can easily connect this to the radius of the Earth. And so he did that, and it turns out that he came up with a number of 5,000 stadia. Okay, so phenomenal sort of insight and creativity. The only downside to this, and so he's done sort of a monumental observation, done the first calculation of the Earth's diameter. The only downside is that we don't know what a stadia is. Okay, it turns out that now we have the luxury of modern units of measure that people agree on. Some people still disagree about whether to use the English system of units or the metric or SI system of units, but we at least know how to convert those. Unfortunately, back then, there was much less standardized, and so his chosen unit of measure was a stadia, which again, they weren't very creative in their naming schemes either. That was the size of a stadium. Okay, but which stadium? And unfortunately, we don't know. And so people have tried to have estimated what a stadium would have been. There are some surviving, some ruins of Roman and Greek stadia that we still know about. So we have some idea about how big these things typically were, but there wasn't a standard size. And so as a result, we don't know how good his measurement really was. We know it could have been as close as within 1% of the true value, which would be really just astonishing. It might be as far away as 15-ish%, but really that's still astounding. I mean, it really is just phenomenally good that he would have had the insight to sort of just make these very simple observations, do a little bit of geometry, and figure out to a very good approximation how big the Earth really is. So, and this is just a little bit more detail on the math itself, which I'm sure is exactly what you wanted to see. Okay, so I want to spend a few minutes now talking about a concept which was developed first by the ancients and which continues to exist as a concept today, but with a vastly different understanding. And it's a concept known as the celestial sphere. So if you read any of the ancient writings, you have to go back far enough, but the early understanding of stars was that they were kind of stuck up in or existed in a very large sphere which surrounded the Earth. So the Earth was in the center of everything, and somewhere very far out there, nobody really knew how far, and frankly, I don't know if anyone speculated how far. But there was a sphere of blackness out there in which the stars and planets, for that matter, which were referred to as wandering stars, which we'll get to, they lived. And so they didn't know, so they knew the Earth was spherical, right? We've talked about that. Eratosthenes established that, not just that, but the size of the Earth even. But they didn't know that the Earth spun, right? Because it turns out that the Earth's rotational speed is small enough relative to its size that we don't notice that unless you make careful measurements. And so they would, but you can't help but notice if you spend any time looking at the sky that the sky appears, that the stars move, and with a few exceptions that we'll talk about, namely those wandering stars, the vast majority of the stars move in a regular, predictable way. They rotate. They appear to rotate in the sky, and so the natural inference is that, well, the Earth, we're just sitting here minding our own business on Earth, and the sky is rotating around us. And so, and by the sky, I mean the celestial sphere. So the ancient Greeks believed that the Earth was stationary. It was spherical, but stationary, and it was surrounded by this large rotating sphere of stars called the celestial sphere. And that explained the vast majority of the bright lights out there. But they were smart enough and paid close enough attention to realize that there were a few stars, lights in the sky, that move differently. Okay, and so they had to be dealt with separately. And so, in particular, the sun, the moon, and the planets each had their own separate sphere, which rotated independently of the celestial sphere. So essentially, you've got a celestial sphere, and then you've got separate sun sphere, moon sphere, and planet spheres, because they recognized that those spheres did, almost all of the dots in the sky move together, but the sun, the moon, and the planets were different, and so they had to be dealt with separately. Now, when you think about astronomy, when you signed up for this class, you probably thought about constellations. I mean, that's one of the first words and first concepts that comes to mind when people think about astronomy. But unfortunately, as I've mentioned in a couple of different contexts already, the definitions of terms in astronomy evolve with some frequency. And it turns out that a constellation is almost certainly not what you thought it was. Not anymore, anyway. In particular, a constellation, according to the modern definition now, is one of 88 distinct regions of the sky. Okay, so it is not, whereas, and that needs to be contrasted with what's known as an asterism, which is a recognizable pattern of stars. So if you think the Big Dipper, the Little Dipper, Orion, things like this, these are largely asterisms, okay? Which, as it turns out, historically would vary from culture to culture. You know, the Big Dipper might have been an asterism that was recognized by the Greeks, but not by the Mayan, and so on. So there's variation across cultures between, you know, what asterisms were recognized. But a constellation now is just one of 88 regions of the sky. And so essentially what astronomers have done is they've taken the sky and they've carved it up into 88 regions. Much like you can imagine carving up the United States, you know, the continental US, into the 48 states. Okay, so if you point to any point in the sky, it will be inside a constellation, just like if you point to any region of the any point on the map of the United States, it will be within one of the 48 continental states, and that's it. Okay, now, so this is an important point to distinguish between constellation and asterism. When I say constellation, I mean one of these 88 regions of the sky. When I say asterism, I mean a recognizable star pattern. Now, to further complicate it, unfortunately, constellations are often named. Each one of these 88, you know, regions of the sky is named, and they're often named after the most prominent star or star pattern within them, which means that you can end up with situations where you have a constellation that has the same name as an asterism within it, just because that's the most recognizable, you know, sensible way to name that constellation. So and to further complicate things, as a practical matter, even professional astronomers will use the term constellation sometimes when they really mean asterism. So I don't want to get hung up on this fact too much, but it will be important for you to at least know in principle, a constellation is one of 88 regions of the sky. An asterism is a recognizable star pattern. Okay. So, for example, Orion is a very well-known asterism and constellation, as it turns out. And so I admit that I like looking at the sky. And when I look at the Big Dipper, I can look at that and say, yeah, that looks like a dipper. For the vast majority of asterisms, when I look at them and somebody says Orion, this is a hunter, I look at this and I don't see hunter. But my imagination is not my greatest feature, so no doubt it's a shortcoming on my part. I can look at these three stars known as Orion's belt and say, okay, well, if I had to represent a belt in stars, I guess it would probably look something like that. But because these asterisms, these star patterns are, they're kind of, they are in our minds, right? So some things are more obvious than others, but what you will recognize when you look up in the sky and you see the brighter stars, and your mind kind of tries to make sense, put them together in some ways. How you put them together will depend upon the kinds of things you think about. And as I mentioned, lots of different cultures around the world and civilizations have done astronomy, have done this, gone through the same process of sort of organizing the sky and the stars into different patterns. But they choose different patterns because they have different, they think about different things, and they have different ideas about where the world came from and so on. Certainly for the ancients, they worship different gods and things like that. And so they're, if they're going to name patterns after a god, the Mayans aren't going to choose the same god as the Romans. So I will recommend, there's a short video here, the link included here, that kind of shows some of these effects. It's short, and so I do recommend you take a look at that. And it's embedded here in the PowerPoint, but I won't take your time during the narrations to make you watch that. So as I said, there are 88 constellations in the sky. And this is kind of shows how it's broken up. It would probably be clearer if the lines weren't blue, but squint and put your nose to the screen and maybe you can make some sense out of it. We're certainly not going to be memorizing the names of constellations or asterisms for that matter, for better or for worse. What you would learn in an introductory astronomy class has changed somewhat over the last several decades. I suspect there was a time where that's exactly what you would have done. You would have memorized lots of different constellations or asterisms and learned where they were relative to one another in the sky and what the most prominent stars were in each one. That is not what's in the curriculum anymore. Now it's much more about classifying the universe and understanding how parts of the universe interact with one another. If this sounds more like physics than you were anticipating, well, yes, it does. So I introduced the concept of the celestial sphere, and we mentioned that to the ancients, they believed the Earth to be fixed, spherical but fixed, and it was surrounded by this celestial sphere that rotated in space. Now, we obviously know that that's not the case anymore. We know that, in fact, the Earth is rotating, and we know that there's no such thing as a physical celestial sphere out there at some distance from the Earth in which these stars are sort of embedded. Nonetheless, it continues to be a useful way of visualizing the night sky and gives us a language of speaking about it. So, in particular, let's introduce a few more terms. So if we imagine an observer standing on top of the Earth, and of course, if I say on top, well, what does that mean? Well, it's kind of defined by wherever he is, right? So he's standing on Earth, not to scale, because otherwise he'd be enormous. But the point, if he looks straight up, so you go out on any night, or day for that matter, though you can't see much then, and you look straight up, that point is known as your zenith, okay? So, and that zenith obviously depends upon who the observer is, because, if Eratosthenes is in Alexandria, he has one zenith, and if he's in Syene, he has another zenith, right? In Livermore, there's a particular zenith, you look straight above Livermore, but if you're in San Francisco, it's going to be a little bit different. So the zenith it's dependent upon where you're observing from, but it's just a fancy name for the point directly overhead. And so perpendicular to the Earth's surface. So you just shoot a line straight up, and that's your zenith. Okay. The celestial poles are points of intersection of the Earth's axis with the celestial sphere. So in other words, that just means if you were standing on the North Pole and you looked straight up, your zenith would be the North Celestial Pole. Okay, so another way of thinking about it is if you have a sphere, you have the Earth, and you have the North and South Pole sticking out. If you just extend that North Pole out until it hits the celestial sphere, that point where that intersection occurs is the North Celestial Pole. And similarly, the intersection of the South Pole, its extension with the celestial sphere, is known as the South Celestial Pole. So if you were wondering, or even if you weren't, it just so happens that there is a star very near the North Celestial Pole that is known as, wait for it, the North Star. So the North Star just happens to be located for us here on Earth very near the Earth's North Celestial Pole, and so it's a useful point of reference for us then. There is no star that is at least particularly bright that is near the South Celestial Pole, and so that's why you don't hear about a South star. So importantly, the celestial poles do not appear to turn in the night sky. Okay, instead the sky appears to turn around these fixed celestial poles, and so that's why if you look up at the North Star throughout the night, it essentially doesn't appear to move, while all of the rest of the stars appear to rotate around it. And that's because to the ancients, they just recognized that fact, and they said, aha, that star, the North Star looks like it doesn't move. We now know that that's because the Earth is in fact moving, rotating around its axis, but the North Star happens to just be along the Earth's axis. And so its apparent location in the sky doesn't change. So this is a great image, I think, that just shows, it's a time-lapse photograph, so it shows a very long exposure throughout the night that shows the stars appearing to rotate around the celestial pole. And I do recommend, there's a nice web-based demonstration of this rotating sky, with a link here that I recommend you take a look at. One other thing that I think we'll come back to and see again, but the location of the celestial pole here. So if this is, I actually don't remember where I took this image from, so I don't remember off the top of my head whether this was in the northern hemisphere or the southern hemisphere. But assuming it was in the northern hemisphere, this would be the north celestial pole right here at the, in the center of these concentric circles. It's the part that's not rotating. And so the North Star would be, right there in the middle somewhere. For what it's worth, the North Star is actually not particularly bright. It's bright enough to see, but it's not one of the 10 brightest stars in the sky, for example. But what's interesting is that if you look at how high up off the horizon the celestial pole is, say you were to measure this angle and it was 20 degrees above the horizon, what that would tell you is that you're at 20 degrees north longitude. And so as you walk, the farther north you walk, the higher in the sky the north celestial pole would get. Eventually, if you get to the North Pole, then the north celestial pole is at an angle of 90 degrees directly overhead at your zenith. So another term to introduce is the celestial meridian. So, and that just means it's the great circle, if you will, that passes through both the celestial poles and the zenith. So it just means you take the biggest circle you can form in the celestial sphere that connects the south celestial pole, goes through the zenith, and then terminates at the north celestial pole. It's called the celestial meridian. And finally, the celestial equator is just the projection of the Earth's equator onto the celestial sphere. So in other words, if you just take the Earth's equator and then expand it out until it hits the imaginary celestial sphere, that's known as the celestial equator. So these are just terms that are useful for sort of navigating the night sky and telling, if you're talking to your friend about, this particular star or asterism or constellation, where they are at different times of night or different times during the year. These are some terms that give you a way of sort of sharing information like that. As I said, we're not actually going to do a whole lot of that during the course because that's not going to be our focus, but it's important to know kind of the fundamental concepts. Okay, so let's look at some examples of how some of this plays out. So let's imagine that you're standing on the North Pole looking directly at your zenith. In other words, the North Star or the North Celestial Pole. And you're watching the movement of the stars. So it would be cold, right? But imagine that you're bundled up warmly enough that you're standing there looking directly up overhead and just, you're not getting tired. And the question is, well, what would you see? Okay. And as it turns out, what you would see is this. So the North Celestial Pole is directly overhead at your zenith. And so that would be the North Star, happens to coincide with that celestial pole. And so it would stay stationary. But then as the night passes, the Earth would be rotating. You wouldn't feel that rotation, so it would look to you like the sky was rotating, and you would see those stars sweep out counterclockwise rotations around the North Star, okay, or the North Celestial Pole. And that's the one thing that I do want to drive home here, is that it would be counterclockwise in the northern hemisphere. Okay. So the North Pole, the North Star, the North Celestial Pole stays at rest, but all of the other stars rotate around it in a counterclockwise fashion. So now since we're at the North Pole, we might as well make as many observations as we can because it's not hard, it's not easy to get back. So now let's say your net gets stiff, so you stop looking directly overhead as your zenith. Now you look at the horizon. What do things look like there? Well, the stars are still rotating around the North Celestial Pole, but now you're not looking at the North Celestial Pole, it's just right overhead. And so if you look at the horizon, you know, and you look past this polar bear there, you see the stars moving from left to right, parallel to the ground, right? Because they're just moving in very large circles whose center is the North Celestial Pole. But again, you just don't see that in your field of view here. Okay, so now imagine that you're standing on top of this building. Now, this is a little bit clearer what it meant when I was giving these lectures live and in person on campus. So you knew exactly what this building was. But assuming that you are watching this from somewhere in Northern California, near-ish Livermore, this will still be true. Imagine you're standing on top of a building there and you face north and you're watching the stars. Question is now, what do you see throughout the night? And as I mentioned a couple of slides ago, now what you see is the following. So you see the North Celestial Pole, it's fixed, and it's at an angular height equal to the latitude of your location. So Livermore's latitude happens to be 37.7 degrees north. And so what that means is that the North Celestial Pole, or the North Star, is located at an angular height of 37.7 degrees above the horizon. So that's your fixed point. That's the point that doesn't rotate throughout the night. Everything else will rotate around it. So if you have stars that happen to lie near the North Celestial Pole, they will rotate in complete, you'll see the complete circle throughout the night. As you get farther away from that star, the circles get bigger and bigger. Eventually, you get far enough away that some of these paths go below the horizon. And so these are stars that you won't see the whole night. You'll see part of the night, and they may rise at some point, they may set, and set at a different point. And of course, once the sun comes up, then you don't see them at all. But the point is that you have this cool feature that you can actually, if you got dropped off or you found yourself in the middle of nowhere with complete amnesia, except for this fact, then you could figure out at least what your latitude is on the globe by finding the North Star and figuring out how high off the horizon it was. Hopefully that never actually becomes practically useful to you. So what does the sky look like at a 30-degree north latitude, for example? Well, from positions other than the poles, the part of the sky that you see is constantly changing. So if you're standing on the North Pole, for example, then there won't be any stars that rise or set. Okay, everything will just move in circles around the North Celestial Pole, and you'll see the same stars all night. They'll just be in different parts of the, in different directions relative to you. But if you're anywhere other than the poles, then the part of the sky that you see is constantly changing. Some stars are rising, other stars are setting, and so it changes. And what parts of the sky you can see then also change as seasons go by. And so that's why, if you particularly enjoy looking at Mercury, there are times throughout the year that you'll be able to see Mercury at night, and then there are other times where you won't. And the same is true for almost everything else in the sky. And of course, if you're at 30 degrees north latitude, the North Celestial Pole, aka North Star for us, will be located 30 degrees off the horizon. And some of the coolest pictures, astronomy has great pictures. My background is in theoretical physics, and we don't produce great pictures, but astronomy gets some really great pictures, and these are some of my favorites: star trails. And particularly if you take them with some really cool foreground, like here, it looks like probably got some lava there. I don't know where this was actually taken, but it's a long-term exposure. And so what's interesting is these were taken at night. Otherwise, you wouldn't see the star trails at all. But it looks like daytime in the foreground, just because in order to get a picture like this, you have to basically set up your camera, open the shutter, and then leave it open, right? For those of you that aren't photography experts, of which I am not either, but the way a camera works, it opens its aperture. It takes for typically something like 1/60th of a second, very short time, lets in light just for that time, and then forms the image from that light. The reason you want a relatively short exposure time is that things will move and they'll blur your image, right? But if you want to take a picture of star trails, you have to leave the aperture open. You have to, leave the exposure. You have to let the exposure occur over a very long period of time, because you need to allow the stars to move far enough that you actually get this trail image. Well, if you do that, then you've got these mountains here, which and things which are actually very, very dark when this is being taken. If you were just there, next to the camera, you wouldn't probably see these things at all. So very little amount of light is coming off of these things. But if you leave the exposure, if you leave the aperture open and you collect that light over the course of 8 hours, well, eventually it adds up enough that you actually see something, and you see something that looks like daytime. So it's a pretty cool, thing in the sense that you say, well, pictures don't lie. Well, there's a sense in which that's true, but nobody ever saw anything that actually looked like this. It's a composite image formed over a long period, long exposure time, but it's pretty cool, I think. So now that you're experts in understanding how the sky looks and changes based upon your location on Earth, let's take a look at the following example. So the question is, which of these images was taken at the equator? So I'm going to give you 30 seconds or so to ponder this. And of course, if you want more time, you can just pause me, and silence me to your heart's content. But then I'll come back and we'll see what the answer is. Okay, well, what do you think? We've said that when we look at the North Celestial Pole, for example, in the Northern Hemisphere, the location, the angular elevation of that point off the horizon is equal to one's latitude, right? So if you're at the equator, the latitude, you're at 0 latitude, which means that the North Celestial Pole, and for that matter, the South Celestial Pole, will be right on the horizon, okay? And as it turns out, that's exactly what we see in image A. So I can't tell you whether image A is taken looking at north or south from the equator, but it's taken from the equator because the celestial pole about which all of these star trails are centered is directly on the horizon. So object or picture A is certainly taken at the equator. Image B looks quite different, but let's imagine what would happen if you turn to the right or to the left. You can see these star trails are tracing out circles, but you're underneath the circle. It's passing over your head. So the question you should ask is, well, what's the center of that circle, essentially? Well, if you turn to the right or to the left, what you're going to see is exactly image A, essentially. Okay, so image B is also taken at the equator. It's just that you're looking either east or west instead of north or south. If you stand on the equator and you look north or south, you see a celestial pole and the stars circling that. If you look east or west, you see the stars coming straight up over the horizon, much like you do in image B. Image C is obviously not at the equator, because you could measure, there's some angular height of the celestial pole. You know, 20 degrees or something like that. So this is taken, you know, if it is 20 degrees, then it's taken at 20 degrees latitude, whether north or south. We don't know. We would have to know, are you in the northern or the southern hemisphere? But we know we're not at the equator. And then finally, D, you can see this is a different image. You're obviously not looking right at a celestial pole, but you see that the star trails are not coming down perpendicularly to the ground, to the horizon. And that tells you that you're not at the equator either. And so the answer is that 2 of the images are taken at the equator, and those are A and B. So what does the sky look like at the equator as you go throughout the night? Well, this is kind of, if you take a second just to kind of make sense of the schematic here, you've got the Earth here. This is the NCP, stands for North Celestial Pole. So the Earth is rotating about counterclockwise as viewed from above the North Celestial Pole. And at 6 p.m., we've got, you know, a guy up here, and the Earth rotates, and so, you know, in 12 hours, he'll be down here at 6 a.m. At the equator, all stars rise and set each day. Because, you know, if you remember back to image B, and I won't go back now because it makes the recording kind of difficult if I'm hopping back and forth, but you're welcome to pause and go back to look at image B in the prior slide. You'll see those stars were coming straight up over the horizon and would be going over our heads then. And that would happen. And so you have the stars rising and you have the stars setting every day. And every star does that because every star throughout the sky is making either a larger or a smaller circle throughout the night, just depending upon where, you know, its relative location. But all of them rise and set. There aren't any that stay visible all night. And whereas if you look at the North Celestial Pole, it's on the horizon, as we said, because you're at 0 degrees latitude. That means that the North Star is 0 degrees above the horizon. In other words, it's right on the horizon. And so if you look close to it, you'll see these stars making either smaller or larger half circles around it as the night goes on. But again, all of these stars will rise and set during the night. And so just a couple of cool images of the North Star from a couple of different locations. At left, we're in the Canadian woods, relatively far north, and so the North Celestial Pole is relatively high above the horizon. Whereas if we go farther south, in this case into Utah, you can get a pretty cool image of the North Celestial Pole through a desert arch there. So lots of opportunities to take great pictures. Just get yourself a camera that you can leave the shutter open and find clear skies, and you too can be a pro photographer. So we're going to finish with just a couple of slides here about locating stars, which, as I said, is not going to be something we're going to spend very much time at all on this semester, but it is an astronomy class, and somehow it feels like it would be wrong to send you, on your way without any recognition of stars and relative locations. So in this case, I thought we would just mention the Big and the Little Dipper, because these are ones that the Big Dipper in particular is pretty easy to find. Unless you're like in the middle of a city with massive light and or other forms of pollution, if you have anything close to a dark sky and you're in the northern hemisphere, you can usually find the Big Dipper. Not all of the stars are equally visible, but they're visible enough that you can make it out. And in particular, you can find, these two stars that are sort of form the edge, the outer edge of the Dipper part, are relatively bright, so those are easy to find. The Little Dipper is much harder to find, as a matter of fact. In fact, some number of those stars are very often not visible at all with the naked eye, unless you are out in a very dark environment, which is harder and harder to find. So if you want to find the Little Dipper, what you can do is start with the Big Dipper, find that, and then these two stars are very often known as the Pointer Sisters because, before we get to that, just as I said, Polaris, the North Star, is relatively bright. I mentioned it's not one of the brightest stars in the sky, but it is relatively bright. That is one that is certainly visible unless it's just very, very bright or cloudy, or something like that. But a lot of the rest of the Little Dipper, you will not be able to see well, or even at all, unless you really know where to look. And so to find the North Star, if you know where the Big Dipper is, you find these two stars on the edge of the Big Dipper, and you point, so thus the name Pointer Sisters for these stars. You point from the lower corner of the Dipper through to the upper corner, and you continue on in the sky until you hit another star. And basically the next star that you will notice with the naked eye is the North Star. And that happens to be the end of the Little Dipper. And so once you find that star, then maybe you can squint, or you can, kind of do your best to see if you can make out the rest of the Little Dipper. As I said, it can be hard to find, but it's there. And if you're navigating, you don't need the Little Dipper, you just need the North Star, right? So in practice, this is by far the easiest way to find the North Star. And then once you know what direction north is, then you're oriented, and not all of your problems are solved if you're lost, but at least you've got a starting point. One other thing to notice is that both throughout the night and certainly throughout the year, the orientation of the dippers will change. So sometimes you'll see them right side up, and sometimes you'll see them upside down, and sometimes you'll see them kind of in between. But the procedure that I just outlined for you will always work. So if you happen to go out sometime at night during the year and you see the Big Dipper looking like this, don't worry. If you want to find the North Star, you still find these two, the Pointer Sisters, these two stars at the edge of the outer edge of the Dipper part, and you follow a line through the sky, and the next bright star that you find is the North Star. So there you have it. Anytime you get lost, your problems are solved now, at least the immediate one of figuring out what's north. So that's going to wrap up this lecture. Thanks for your attention again. As always, if you have any questions, feel free to post to the class website or get a hold of me otherwise, and I will see you back here for lecture 4.